Good morning to all of you. In previous session, we have seen four theorems of Fourier transform, that is linearity, time shifting, time reversal, and convolution theorem. In today's session, we will be discussing correlation theorem and its modified version, which is for finding the autocorrelation, or also it is called as the energy spectral density. So basically that theorem is called as Wiener Khintchine theorem. So these two theorems we'll be discussing, that is correlation theorem and Wiener Khintchine theorem. Okay. So first we'll discuss the correlation theorem. So basically this correlation theorem is for identifying the cross correlation of the given signals. As we have already seen, the cross correlation of two signals, just for example two discrete time signal, that is x of n and y of n. So these are two distinct signals, so its cross correlation is indicated as rxy of l, and the formula for identifying this cross correlation is summation n is equals to minus infinity to infinity x of n into y of n minus l. Okay, so this is the cross correlation formula that we have already seen when we have discussed the cross correlation topic, right? So as per the correlation theorem, if we have two discrete time signal, that is x1 of n with Fourier transform capital X1 of omega and x2 of n with Fourier transform x2 of omega, right? Then the cross correlation of these two signals, which is nothing but it is indicated as r x1 x2 of l, just for example, right? So this is nothing but the cross correlation of x1 and x2, right? So cross correlation of signal x1 of n and x2 of n, which is indicated as r x1 x2 of l. Okay, so in Fourier domain, okay, so before that I will write the formula for the cross correlation of these two signals. So we have summation n is equals to minus infinity to infinity x of n into y of n minus l. Okay, so in Fourier domain, this cross correlation will be simply the multiplication of the Fourier transform of x1 of n and x2 of minus omega. Okay, that is phase reversed version of the Fourier transform of x2 of n, right? So in Fourier domain, we can indicate it as by, just for example, capital S of x1 x2 of omega, right? So this is nothing but the correlation theorem, right? So this is how we can identify the correlation of given signals, that is x1 of n and x2 of n. Okay, so this r x1 x2 of l, right, can be simply represented as just for example, if instead of taking this as r x1 x2 of l, I will just use some other variable there, right? So in place of l, if I'm using n, and in place of n, if I'm using l. Okay, so I can write it down it as r x1 x2 of n is equals to summation l is equals to minus infinity to infinity x1, it should be x1 and it should be x2. Okay, so x1 and x2, so x1 of l multiplied by x2 of l minus n. Okay, so this is nothing but the cross correlation formula. Now we are interested in identifying the Fourier transform of this cross correlation signal, so it should be x1 of omega multiplied by x2 of minus omega. So we are trying to prove this property, right? So the Fourier transform of this r x1 x2 of n, okay, so I can indicate it as this capital S x1 x2 of omega, and this can be given as summation as per the Fourier transform formula, summation n is equals to minus infinity to infinity x of n. So in place of x of n we have r x1 x2 of n multiplied by e to the power minus j omega n. Okay, so that is the formula for Fourier transform. So I'll just rewrite this equation on next slide. So we have this capital S x1 x2 of omega is equals to summation n is equals to minus infinity to infinity r x1 x2 of that n, right, multiplied by e to the power minus j omega n. Okay, the reason for exchanging these variables here, so basically L is replaced by n and n is replaced by L in this case, because in the Fourier transform formula we are taking n variable here, right? So n is equals to minus infinity to infinity x of n into e to the power minus j omega n is there, right? So therefore this n variable has been exchanged with the L variable. Okay, so now we'll substitute this value, okay, of r x1 x2 of n in that formula. So we will have this n is equals to minus infinity to infinity. In place of r x1 x2 of n we can substitute L is equals to minus infinity to infinity x1 of n. So summation L is equals to minus infinity to infinity x1 of L multiplied by x2 of L minus n, okay, L minus n multiplied by e to the power minus j omega n, right? So this we have here, right? So I can take this summation at L is equals to minus infinity to infinity x1 of L outside this summation limit, right, and multiplied by summation n is equals to minus infinity to infinity. So n summation I have taken inside, so it is x2 of L minus n into e to the power minus j omega n. Okay, so here you can see as per the time shifting property, so it is n minus L basically, right? But for applying the time shifting property here it should be n minus L. So if it is n minus L, so we can write as we know that as per the time shifting property, if x of n has the Fourier transform x of omega, okay, then x of n minus k has the Fourier transform e to the power minus j omega k into x of omega, right? So this is as per the time shifting property. So if you compare this equation with what we have here as per the time shifting property, so here it should be n minus L. Okay, so as negative sign is there, so it is basically minus of n minus L, right? So while applying this time shifting property in place of k we have L here, but the here it is minus k, but here it is positive L. So as per time shifting property we can write this first term will be as it is x1 of L, okay, multiplied by, so this as signal is x2 in place of x of n, signal is x2, so its Fourier transform will be x2 of omega. Okay, but as we can see here this omega as this x2 it is basically time reversed, right? uh, because this negative sign is there, as we can rewrite this x2 of L minus L as x2 of minus of n minus L, right? So obviously the Fourier transform of this x2 will be x2 of omega, that is x2 of n minus L if there, then you can directly write down x2 of omega, but as it is time reverse, so it will get phase reversed, right? So it will be x2 of minus omega, correct? So similarly here we can write e to the power minus j omega L, okay, multiplied by e to the power minus j omega L. In place of k we have L here, right? So therefore it should be e to the power minus j omega L. So again, if you observe this particular equation, so this is nothing but the equation for the Fourier transform. Simply in place of n, variable L is there, right? But it is nothing but the Fourier transform of x1 of n, right? So the Fourier transform of this x1 of n can be represented as x1 of omega. So it will be simply replaced with this x1 of omega multiplied by x2 of minus omega. Okay, this is nothing but the cross correlation of the given signals, that is x1 of n and x2 of n in the Fourier domain, okay, or frequency domain. Okay, so this is what we want as the proof, right? Okay, so this is nothing but the cross correlation or correlation theorem. Okay, but when we are referring this cross correlation in terms of autocorrelation, basically this cross correlation is also called as this equation, that is as x1 x2 of omega is also called as cross energy density spectrum. Okay, so this as x1 x2 of omega is also called as cross energy density spectrum because it is the cross correlation and it is represented in the frequency domain, so therefore it is the energy density spectrum. Okay, but when we are identifying the autocorrelation, okay, so autocorrelation formula, as we have already seen before, as in this case the cross correlation formula is this one, okay, that is rxy of L, right? So the autocorrelation of x of n is simply represented as rxx of L. Same signal is correlated with itself. Okay, so the formula for it is n is equals to minus infinity to infinity x of n into x of n minus L. Okay, so if I am simply representing this as we are represented this cross correlation r x1 x2 of L in the Fourier domain, so it was s x1 x2 of omega. So if I am representing this autocorrelation, that is r x of L in the Fourier domain, so it will be s x of omega. Okay, so this is nothing but the autocorrelation represented in the Fourier domain. So again, it is the energy spectral density of an energy signal is nothing but the Fourier transform of its autocorrelation sequence, right? So the autocorrelation of a signal and its energy spectral density contain the same information about the signal in this case, and this particular theorem is basically called as the uh, Wiener Khintchine theorem. Okay, Wiener Khintchine theorem. So when we are representing the autocorrelation in the frequency domain, so it is the energy spectral density of the signal. Okay, so this is nothing but the correlation theorem. Okay, so we have seen correlation theorem here as well as the Wiener Khintchine theorem. Okay, so let's see one example where we are be identifying the correlation of the signal as this x1 of n and x2 of n has been given. So initially we'll identify for identifying the correlation of this signal, initially we need to identify the Fourier transform. Okay, so the Fourier transform of x1 of n and x2 of n will be simply as it will be indicated x1 of omega summation n is equals to minus infinity to infinity x1 of n into e to the power minus j omega n. So here the limits will be from minus 1 0 to 1. Okay, so minus 1 to 1 will be there, right? So I will directly write down the equation here. So if I'm substituting n is equals to minus 1, so it will be minus minus plus, so it will be e to the power j omega plus x1 of 0 is 1 multiplied by e to the power 0, so it will be 1 plus when I'm substituting n is equals to 1, so it will be e to the power minus j omega. So this is x1 of omega. Similarly, as this x1 of n and x2 of n are same, so therefore this x2 of omega will be as it is, as same as that x1 of omega, so that it will be e to the power j omega plus 1 plus e to the power minus j omega, right? So here as as per instead of cross correlation, as per correlation theorem of Fourier transform, for getting this x1 x2 of omega, this is nothing but in the Fourier domain, and it is the cross correlation or correlation of x1 x2, okay, in frequency domain. So we need x1 of omega multiplied by x2 of minus omega, right? So we have this x1 of omega, x2 of omega, so wherever there is omega we will replace with minus omega, right? So again we'll get the same equation basically, right? Because here if we are replacing minus omega omega with minus omega, so omega this minus minus will be plus and it will be minus in this case, okay? So we'll simply multiply here this as x1 x2 of omega is equals to, we'll have in first bracket 1 plus e to the power minus j omega plus e to the power j omega, and in another bracket the same equation, because only these signs will get exchanged. So 1 plus e to the power minus j omega plus e to the power j omega, right? So after multiplication x1 x2 of omega, so when we multiply it, so again you can multiply 1 with whole bracket, so 1 plus e to the power minus j omega plus e to the power j omega, then e to the power minus j omega with complete bracket, so e to the power minus j omega e to the power minus j2 omega plus e to the power 0 plus again e to the power j omega plus e to the power 0 plus e to the power j2 omega. So if I add all these values, right, so this 1 plus 1 plus 1 will be 3 plus e to the power minus j omega e to the power minus j omega, so 2 e to the power minus j omega e to the power j omega e to the power j omega, so 2 e to the power j omega, and the remaining term e to the power minus j2 omega plus e to the power j2 omega. Okay, so again I will write these so that I can take the inverse Fourier transform it. So I will write here e to the power j2 omega plus 2 e to the power j omega plus 3 plus 2 e to the power minus j omega plus e to the power minus j2 omega. So by taking its inverse Fourier transform, what we will get r x1 x2 of L. Okay, so it will be simply the coefficients of this equation. So it is what 1 comma 2 comma 3, so 3 will be origin, then again 2 comma 1. Okay, so this is the required correlation. Okay, this is the correlation with the x1 of n and x2 of n. Okay, so this is how you can use this correlation property of the Fourier transform to identify the correlation of the given signals. Okay, so in today's session we have discussed the correlation theorem as well as the Wiener Khintchine theorem. So in next session we'll be discussing the frequency shifting property as well as the modulation theorem. Thank you for joining this session.